talking about molecular dynamics and protein hydration as studied by solid-state NMR, I will use the various concepts that I have introduced. Okay, how do we use solid-state NMR to investigate molecular motion and hydration? I want to first start by showing you a few animations. This is the first example of influenza M2, where a key histidine residue is responsible for shuttling protons from the outside to the inside of the virus. The outside is acidic, so this is a pH-activated or acid-activated proton channel that sits across the lipid membrane of the virus. In this animation, we try to depict the motion of the histidine ring that we studied by solid-state NMR. We measured the motion of the average dipolar couplings on that imidazole ring to deduce the geometry of motion. This is trying to show how ring flip assists the proton transfer from the hydronium ions H3O+ from upstream to downstream through this ring reorientation. Motions like this occur in proteins and, of course, other molecular systems. For proteins, dynamics of the protein side chains are important for many things, such as ion conduction in this case, substrate transport. For other transporters, ligand binding, catalysis all involve motion. This is a second example of molecular dynamics, and this is again about influenza M2 proton channel, but here we're interested in the dynamics of the ligand, which is amantadine. This is a proton channel blocker that blocks M2. Amantadine is this little grease ball, all basically hydrocarbon CH groups and so on. It's a threefold symmetric ring with an NH2 group. And by looking at deuterium NMR spectrum of a deuterated amantadine that is reconstituted with the protein, we discovered how this amantadine is moving, and it's moving in a uniaxial rotational way around the channel axis, sitting inside the 4-helix bundle near specific residues that we also found out by doing read-or measurements. So that's another example of motion whose geometry we clarified by solid-state NMR. So dynamics like this give you a lot of insight into function, mechanism of action, and there are many protein motions, internal motions that exist. And I want to just highlight some obvious ones, such as methyl group rotations, 3-side jumps, also amine group, 3-side jumps, NH3. And then there are a lot of side chain torsional motions. You can have side chain rotameric jumps of, for example, hydrophobic amino acids such as leucine that can undergo typical rotameric jumps between two highly populated conformational states, MTTP. You can have more traditional trans-Golgi isomerization for long aliphatic side chains such as lysine and arginine before you get to the polar ends of these amino acids. If you have aromatic rings, such as tryptophan, tyrosine, and phenylalanine, less so for tryptophan because the indole ring is a bit bulky, then you can certainly have ring flips. Then there's the general backbone torsional fluctuations that one can detect by NMR. And then there are larger amplitude motions of loops and termini that one can study. And then stepping out of the internal motion realm, you can think about global motions that a whole protein can undergo. And for membrane proteins that my group is particularly interested in, we often see uniaxial rotational diffusion of helical bundles or maybe 7 transmembrane helix proteins, which other groups have studied. That uniaxial rotation is basically spinning sort of a cylindrical shaped membrane protein in a 2-dimensional fluid of lipid bilayers. And as long as your membrane protein is not too bulky, in other words, the footprint is not too large, then this uniaxial rotation happens relatively easily. Okay? If your footprint is too large, then it gets difficult because that motion will have to involve replacing a lot of lipids and so on. But for smaller membrane proteins, this happens easily. There are also correlated motions of protein domains, which I won't go into. This is a bit of an outline. Studying molecular motion by NMR is obviously a very big and very deep topic. And I have a certain emphasis on which aspect that I find particularly interesting, particularly easy to visualize. And that is, for me, always the geometry of motion, the amplitude of motion. So I won't say too much about rates of motion because I think that's the realm of relaxation NMR that a lot of other people can speak more knowledgeably about. And I will emphasize how fast motion average the NMR couplings or NMR line shapes. And from that kind of fast motions by measuring the order parameters, or in other words, reduction factors from the rigid limit, then I can deduce which way your side chains are moving, which geometry. And that I think is the most interesting aspect. So molecular motions can average NMR line shapes. They can enhance peak intensities if you narrow your line shapes enough, or they can reduce peak intensities if the motional rate is awkward at an intermediate time scale that will reduce your spectral intensity. Generally, molecular motions are the mechanism for relaxation. If you don't have anything, then you have a rock solid and then nothing drives relaxation. When you have motions, then if you want to ask the question of quantification, how much of certain species do I have in my sample? And I want to be able to tell that from the intensity. Well, if you have motion, then your intensity is no longer easily quantifiable. All right, so that complicates this aspect of NMR. On the other hand, having molecular motions can allow you to do some spectral editing. If you have a dynamically heterogeneous system, and you don't want to be looking at everything in the same spectrum because it's too complex, then you can selectively detect the rigid species or selectively detect the dynamic species. So having different motions going on is a very nice knob you can turn to do spectral editing. So I'm going to first talk about, on a very general level, the time scales of motion and what is the language we use to describe the amplitude of motion. And then I want to go into the study of fast motion, fast, slow, intermediate. I want to first talk about fast motion. How would you characterize it by NMR? And I want to use a tensor-based approach, thinking about the chemical shift tensor or average dipolar coupling tensor. So using NMR interaction tensor, but now it's average tensor, average by motion. I want to use that as a way of thinking about what kind of frequency spectrum you should expect. And then I will talk about what kind of solid state NMR, magic angle spinning experiments are available that are relatively straightforward to use to measure fast motion. And then I want to switch to the very slow kind of motion, things that are happening in tens of milliseconds or slower, hundreds of milliseconds. And what would be the approach? And again, using interaction tensors, the trick is the gist of this is to think about difference tensors. And then a little bit about experiments for measuring slow motion. So I skip intermediate time scale motion because that's really the most complicated thing to measure, to observe, to analyze, so that I don't cover. And it's also less studied for the reason that, it's hard to study. Okay, rates and amplitudes of molecular motions. This is a very elementary description. The motions that we normally look at are stochastic, random motions. And to describe stochastic processes, you want to use the mathematical formalism of correlation functions, which are defined in this way. C of t is proportional to a property, a function at time 0 versus time t later. And you want to see how this motion actually starts to move this function away from its original state. And you describe that by looking at the product of the f0 with ft and then doing this averaging. So this describes how long it takes for that random motion to randomize the molecular orientation. So the C of t, once you have that correlation function established, then you can think of your random motion to basically cause a decay in a correlation function with a certain characteristic time constant, tau of c. The correlation function is the formalism to think about just what we mean by the rate of motion. The characteristic time, tau c, describes that exponential decay. So the rates of motion, k, is inversely related to the correlation time, tau c. Now, the amplitude of molecular motion is a very distinct concept. Amplitude describes the reorientation angle. So if a molecular bond has moved because your molecule is doing some kind of reorientation, then the bond will change its orientation to a different new position, initial, final. So then you can describe a reorientation angle beta r in that way. The amplitude of motion implicitly would also have a concept of number of sites involved. The number of sites is important, whether you have simple 2-side jumps, hop to here, back, back and forth, that's 2 sites, or you have 3-side jumps for methyl groups, you have CH3, and the 3 protons will swap positions. That's a 3-side jump. So the number of sites, n sub r, is part of that concept. I should, of course, clarify that in this whole talk about molecular motion as studied by NMR, I'm referring to rotational motion, reorientational motion. I don't speak of translation motion, which has to be studied by a distinct type of NMR, pulse field gradient NMR. Then in terms of amplitude of motion, you can think of two types of motion: diffusive motion versus discrete motion. Discrete, the three-side method rotation or the two-side jumps are discrete. This is a very finite number of sides, 2 or 3. And if you have tetrahedral jumps, then it's 4. All right, still a small number. And the reorientation angles are relatively significant. All right, whether you have the method rotation and you're hopping, and the beta angle is in that case 109 degrees. So these are finite reorientation angles. So that's discrete motion. And I have a funneling ring flip as an example. You have a benzene ring and it flips. And when you do that, you might think about this is a 180-degree flip, but the bonds associated with the ring, let's say a CH bond, goes from this direction to that direction. And if you draw out the benzene ring, you look at this, this is 120 degrees. So that's the reorientation angle 120, and the number side is 2. Now that's discrete motion. We can all visualize this in our mind. Diffusive motion is different. That's when the reorientation angle gets infinitesimally small and the number of sides gets infinitely large. And this is what we mean by diffusive motion. And what kind of motions are diffusive? You have isotropic tumbling. You have, when I say uniaxial rotational diffusion of a membrane protein and alpha helix, then that's diffusive motion. Torsional fluctuation often is that way. All right, that's just a bit of a vocabulary for defining what we mean by amplitude of motion. And this is the part that is particularly interesting. Now, the motional regime does matter, even though I am not doing relaxation NMR. You have to understand some basic concept, and that is fast, slow, and intermediate, because this determines what kind of experiments one can do or should do. Fast motion, what is fast? Fast is always the motional rate, K, how that compares with the couplings that you're interested in measuring. You have your motion, it's going to impact your NMR spectra, whether you're measuring maybe chemical shift anisotropy, or maybe you're measuring dipolar couplings. All your couplings, anisotropic couplings, will be narrowed by your fast motion. So when K is much greater than the anisotropy parameter delta, or you might write just generally the difference in frequency, and these frequencies are orientation dependent anisotropic frequency, then that's what we mean by fast. Okay. All right. And the amplitude of fast motions can be obtained by spectral line narrowing experiments. And what kind of experiments? There's the classical deuterium NMR done on static, non-rotating solids. Your molecules are doing some interesting motion, but your macroscopic sample is not spinning. So deuterium NMR is a good way to look at amplitude of motion. But of course, we want to do magic angle spinning so I can resolve a lot of sites. I can get motional information in a site resolved way. And so then there are techniques such as dip shift, dipolar shift, chemical shift correlation experiment, or 2D Lee Goldberg CP experiment, or WISE and various CSA recoupling experiments can be considered. Rates, well, okay, how much faster should you be? And generally, for these spectral line narrowing experiments to work well, you would want your K, your molecular motional rate, to be at least an order of magnitude faster or larger than the coupling of interest. So to get the exact rates, that's hard. Then you need to do relaxation. Let me switch to then the slow motional limit. And this is when K is much less than delta omega. And typically this means the motional correlation time, tau C, should be much longer than 10 milliseconds. If you say, can I measure things in a 1 to 10 millisecond regime? Well, you know, if you have some pulse sequence element that are taking a millisecond to do, then during that time, your molecule is running away from you. And so that is going to cause interference or intermediate motional regime. So that's not convenient. You would like your motion to be slow enough, you know, greater than 10 milliseconds. The amplitude of slow motion can be measured from 2D exchange NMR line shapes. So this is very much equivalent between solution state and solid state. But in a solid state, you have a chance to measure anisotropic 2D exchange spectra. At least in the old days when people actually can still get away measuring really literally static 2D exchange. And if you're spinning, then you have to start thinking about sidebands and so on. But anyways, 2D exchange is the way to go. But a more modern version that is a very nice experiment is a codex that I want to talk about. The rates of slow motion can be obtained by measuring decay constant of an exponential decay process. And that exponential decay is usually monitoring intensity of something. cross peak typically as a function of the mixing time that you wait in these exchange NMR experiments. So that's the way to probe the rates of slow motion. So that's much easier to do than to probe the fast motions. Okay, I want to skip intermediate motion because that's really quite a lot of work to study, and there are not so many techniques to probe that. The first problem is that the intensity would drop, and so it's hard to see. And you can already see that the effect of how motional rates impact NMR spectrum from this set of diagrams or simulations that I got from this paper, R. Palmer, 2004, a review article. On the left is an example of if you have two sites and their population is 50-50, and you have two-site exchange, and if that exchange is rapid, that motional exchange is fast compared to what? Compared to the frequency difference or chemical shift difference, then you get a single peak right in the middle of the two parent frequencies or chemical shifts. And if you have very slow motion, slow exchange, then you get the two peaks, the unperturbed chemical shift. And if you have anything that's in between, sort of intermediate, so K comparable to the frequency difference between the A and B chemical shift, then you get to this very broad hump that is barely visible. So that's something that I think most of you have seen. And on the right, situation changes just a little bit because the population is no longer 50-50. So suppose the molecule occupies one state predominantly over the other state. And if that population is 3-to-1 ratio, then you can imagine that the average chemical shift should be closer to the main conformer A and further from the B. This concept was illustrated with isotropic chemical shifts in mind, but if you have anisotropic frequencies, it's actually a similar concept. Before I go into describing how to think about the effect of reorientations on anisotropic interactions such as chemical shift, anisotropy, or dipolar coupling, I want to remind you of this very important equation. So the anisotropic frequency omega, whether it's chemical shift or dipolar coupling, can be generally written in this way, where you have the dependence on the angle, the powder angle, theta and phi. And in the simplest casting of the equation, the theta and phi describe the polar and azimuthal angle of the magnetic field, B0, in a molecule fixed frame. And the molecule fixed frame, the easiest without doing sample rotation, would be the principal axis system of your chemical shift tensor or your dipole tensor. So this equation you have seen multiple times, and then you have the delta and eta shown in red here, and that describes the anisotropy parameter of the interaction tensor and asymmetry parameter. Okay, so that's all good, and we know that this would be the kind of static powder line shape you should expect when nothing is moving. Right? You have a static, non-rotating sample where the molecules are not rotating, no motion. Now, suppose, don't worry about sample rotation, don't worry about magic angle spinning. But now your molecules acquire some interesting motion, and motion is fast. The first statement we want to make is that fast motion is going to change your anisotropic frequency. You're going to have to change this omega theta phi because your molecule is now rapidly changing its angle theta phi relative to the B0. So reorientation among a number of sites, and there's a probability, Pj, it's going to average your interaction tensor. That's for sure, that's going to happen. In general, you might say, well, how do I get an average frequency? I'm going to do omega time average bar. And in general, this is basically the omega of the individual site J, right? If you have 3-site jump, then you have J equal to 1, 2, 3. And then there's a population in front, P of J. You might think this is how you should figure out what's the average frequency. But this is relatively complicated to do unless you just delegate it completely to numerical simulation. What I want to describe is a way to sort this out by figuring out the average, motionally averaged interaction tensor. Because if I can get that tensor, then I can generate the powder pattern. How do I get the interaction tensor? The average tensor is sigma. I call that the sigma sum or average. And it's going to be the individual static instantaneous tensor, sigma, sub j, pj. And just like any second rank tensor, all you're doing is you're taking individual second rank tensors, you're doing average. So the sum tensor or average tensor should also be a second rank tensor. And if you can figure out all the 9 elements, you should then get 3 principal values or 3 principal axes, just like your normal second rank tensor formalism. And so I'm going to call these 3 principal axes 1, 2, 3, sigma 1, 2, 3. And if you can figure out what is the average tensor property, then you should be able to get an averaged anisotropy parameter delta bar, and you should get an average asymmetry parameter eta bar. And what exactly these are, the delta bar and eta bar, that depends on what kind of motion you have, whether you have a methyl 3-side jump or ring flip or whatever. If you can work out what that average tensor is, what kind of property it has, and which way it is oriented in a molecule, in your molecular frame, then the working out the line shapes becomes quite feasible again, because I can say, well, the anisotropic frequency of any second rank tensor follows this type of equation, omega theta phi equals 1/2 delta 3 cosine square theta minus 1 minus eta sine square theta cosine 2 phi. You rattle it off like that. The only thing that changes is that the angle theta and phi for an average tensor should be associated with that average tensor. So I need to work out what is theta A average, what is phi azimuthal angle average. These are powder angles in general. And then this average frequency should have the delta average and eta average going in there. So theta A and phi A will be your powder angle. The bottom line is I set up this way of thinking to say that once you can figure out the average tensor property, then we can predict the motionally average line shapes, just like what I showed in the basic NMR lecture. If eta average is 0, you know it's going to be the uniaxial powder line shape. If eta average is 1, then it's a 10 shape. And if the delta average tells me how wide that line shape is, then I know basically everything about the system under motion. So in general, delta average is not the same as delta, you know that. Eta average is also not the same as eta. For dipolar couplings, delta average can be sign sensitive. So normally you think of dipolar couplings as not having a sign, but motion can actually give you a delta average dipolar coupling, which has a negative sign. And this would then tell you something about the direction of the average dipolar coupling relative to the molecular bonds. Normally, the rigid limit dipolar coupling is uniaxial interaction. Eta is definition almost 0. But if you have motion that average the dipolar coupling, then that motion can make the eta average non-zero. And I will show you example of that for phenylene ring flip. So you can have an interesting motionally average dipolar coupling that has a line shape, which is not your typical eta equal to 0 line shape. So this is the framework for thinking about it. And now the hard part is, well, how do I find out what is delta average, what is eta average for particular types of motion? How do you determine that? And how do I know what would be the 3 principal axes? What's the direction of these principal axes for the average tensor? How is that related to my molecule, right? My molecule is hopping, is doing some discrete motion, and we need to figure that out. So, okay, how do we determine this? Let me start with the simplest kind of motion you can think of, and we'll work our way to more complicated motions. Averaged anisotropy and asymmetry for a few common motional geometries. If you have isotropic motion, random tumbling over all possible orientation in space, then the delta average is 0. Done. And if delta average is 0, then you know in these equations, this omega average is 0. So you don't have to pursue further this theta A, phi A, or line shape. So it becomes an isotropic peak. You don't have any anisotropy. If you have uniaxial rotation, or if you have Cn jumps with n greater than 3, so 3-side jumps like a methyl group rotation, right, with that symmetry, then both these type of motions, uniaxial has a unique axis, that's what it means to say uniaxial, then these motions have an average asymmetry parameter of 0. And the unique axis points along for the uniaxial rotation is the axis of motion. For the three side jumps, if you have a methyl group, you have a CC bond and you have three CH bonds, then the CC bond is your unique axis, okay? So for these two types of motion, the average asymmetry parameter is 0. That also simplifies the consideration a lot, because you know in this equation, you don't have to worry about what's phi of A, you only worry about theta, and then you still have to consider what's delta average, and we'll talk about that. So, all right, for these two types of motions, the z-axis of the average tensor is the symmetry axis. So your tensor now becomes uniaxial, the average motion average tensor uniaxial. Whenever it's uniaxial tensor, you really just worry about one principal axis. It's the z-axis, okay? And that's the symmetry axis. Now, how do I get the delta average for uniaxial rotation and Cn jumps for n greater than 3? This is a bit of a interesting thinking. I hope I can explain this. First, you have to recognize this point. The principal value of any tensor, the three principal values of any tensor, are the frequencies you get when the magnetic field B0 points along that principal axis, okay? Think of an arbitrary chemical shift tensor. You have your Cartesian coordinate z, x, y, and you have molecules randomly oriented. But if your B0 field happens to be along one of these molecules' z-axis, or in other words, I can turn it around and say, if I have one of these molecules where the chemical shift principal axis z happens to be along B0, when that molecule is going to get a chemical shift that is the omega zz value, you get that principal value. If you go to a differently oriented molecule, orient such that its x principal axis happens to be along the B0, then that molecule's anisotropic chemical shift is the x principal value. All right, so these principal axis directions, these three directions are relatively special. When the magnetic field points along these principal axes, then the anisotropic chemical shift is the principal value of that axis. Okay. I want to show this point again
by invoking this equation about the orientation-dependent chemical shift frequency.
I passed over
you have seen
in
this
my
equation
proof
before, but I
the
skipped the proof.
orientation-dependent chemical. This is a very useful way of looking at anisotropic frequencies because you're writing it in a fairly symmetric way. You have all three principal values explicitly in here, and then each of these principal values gets the sinusoidal modulation in this way, which involves these cosine sine. Yeah, the polar angle, azimuthal angle, the typical thing of this projection of the tensor onto the z-axis, x-axis, y-axis. All right, so that's no problem. And if you look at this equation, then I can show that when theta, the angle between the tensor, the z-axis, and the magnetic field, when that theta is 0, then I get omega cs equals the last term, because only cosine 0 will remain as 1. The sine square theta, when theta is 0, will vanish. So you get a chemical shift frequency of omega zz. Basically, this equation says, okay, that's what happens when your B0 field happens to be along the z principal axis. Then you measure a frequency, which is the zz principal axis. When theta is 90 degrees and phi is 0, that's the situation when the magnetic field is along your x-axis of your Cartesian coordinate, your PS. Then you can work out the chemical shift of the x principal value. And if your theta equals 90 and phi equals 90, then you get omega chemical shift equal to y principal value. This is all fine, and that basically just gives a little bit of proof that the principal values are the frequencies you get when the magnetic field is parallel to those principal axes. Because of that, the delta average that I want to evaluate, I want to be able to calculate this motionally average anisotropy parameter. That must be the frequency when the magnetic field is parallel to the z-axis of my motionally average tensor. So if your B0 happens to be along the unique z-axis, symmetry axis of your motion for uniaxial rotation or Cn jumps, then you will get a delta average. And when the magnetic field is pointing exactly along the symmetry axis, then you can also say, well, my molecule is doing uniaxial rotation around that symmetry axis, but my magnetic field is also along that. Then, because the motion does not really change, the orientation of the PAS relative to the B0 field, because now B0 field is smack along the symmetry axis, then the frequency depends basically on the very fixed theta, PD, P is PAS, D is director, and even the phi PD is the same for this uniaxial rotation or CN jump. So the delta average, then you can just write down according to the normal equation you already have seen. It's equal to omega when the two polar angles are theta PD and phi PD, and these are now fixed angles. This says, okay, then delta average, motionally average, and isotropy parameter is 1/2 delta 3 cosine squared theta PD minus 1 minus eta, etc. So for uniaxial rotation, as well as CN jumps where n is greater than or equal to 3, the motionally averaged anisotropy parameter is this. It depends on the rigid limit delta and eta in this way. And the relevant angles here are not powder angles anymore. They're fixed angles that depend on the motional geometry. They're the theta PD and the phi PD. And we'll give examples of how you get this. So let's try this formalism for some of the easiest or simplest or most common motions that we know. Methyl groups normally undergo 3-side jumps at any typical temperatures unless you go to cryogenic temperature. This is a picture of methyl rotation. If you have a CH3 group attached to another aliphatic group, so you have a CC bond being the methyl rotation axis, and your 3 protons are just swapping positions in a very rapid way. And you know, in this kind of tetrahedral system, well, the relevant bond angle is always 109.4. Okay, so then this is an example of C3 jump. So I can then apply the formalism where I say, okay, eta average for this is 0, because that's dictated by the symmetry, but I still need to work out what's the delta average. And the delta average is then equal to omega of theta PD and phi PD. What is the theta PD? If you want to measure CH dipolar couplings for methyl groups, then you know the CH bonds are rotating around the CC axis, and the relevant angle is exactly the tetrahedral angle, 109.5, right? It's a fixed bond angle. This eta in this bracket is the original tensor's asymmetry parameter. But here I have chosen to consider the dipolar coupling, and dipolar coupling rigid limit eta is 0, so that I don't have to worry about the last term. Okay, so then the delta average is 1/2 delta, and you have 3 cosine squared 109.5 minus 1. Okay, 109.5 is twice the magic angle, and this is one of these nice numbers where the cosine square comes out nicely, and you can show that this whole thing comes out to be minus delta over 3. So it's 1/3 of the rigid limit anisotropy parameter with a minus. Okay. So methyl 3-side jumps will average your CH dipolar couplings by a factor of 3. And otherwise, this motion averaged eta is 0, just like rigid limit dipolar coupling is also eta equal to 0. And this is why simulations shown here for if you don't have any motion going on, then you can say, okay, I get this Page pattern, and this is classical deuterium NMR, but this is basically the same as CH dipolar coupling. Deuterium NMR for CD groups is a tensor which is uniaxial basically along the bond. So the simulations done by Palmer, Williams, and McDermott many years ago, considering deuterium NMR, I say slow limit looks like this. This is the Page pattern, okay? Static sample, non-rotating sample, but the molecule is having the methyl rotation. And if you go to intermediate, you get something complicated. But then if you go to very fast, K, motional correlation time on a nanosecond regime, then all you do is shrink your Page pattern by a factor of 3. A Page pattern comes from uniaxial one way, take this, and then uniaxial another way, take this, and then I add them up. Okay, so this is 90-degree edge. This is the 0-degree edge. I have two components. So both deuterium quadrupole interaction and dipolar couplings have this static peg pattern. But fast method rotation will shrink the line shape by a factor of 3, but otherwise it keeps exactly the same shape. Okay, then you can say, well, that method rotation is very nice, a very highly symmetric kind of motion. Do all my interactions get narrowed in that way in a method group? So the answer is no, because even though the molecule is still moving this way, it's always around the CC axis and these protons are switching positions. But if you say, all right, I would like to measure proton-proton dipolar coupling. I'm not aware of people doing this measurement, but just think about it anyway. Homonuclear proton-proton dipolar coupling. Then what happens? Well, then you have to think about how the rigid limit proton-proton coupling tensor, HH bond, how that is oriented relative to the symmetry axis. And in this tetrahedral group, I hope you can see that these three tripod leg positions, the H, they're in the plane, they're perpendicular to your rotation axis. So the angle between the rigid limit HH vectors and the rotation axis is always 90. Okay. So then, again, the rigid limit interaction is a dipolar interaction, so eta without the bar is 0, and theta PD, the angle between the rigid limit tensor direction and the motional symmetry axis is now 90. Okay, so I will then plug in to this again, and I get delta average equals 1/2 delta 3 cosine squared 90 minus 1. And cosine 90 is easy, that's 0. And so I get minus delta over 2. So if you were to measure proton-proton dipolar coupling of a methyl group, you will find that that coupling is narrowed by a factor of 2. This kind of thinking is all very useful. With this understanding, you can say, okay, autoparameter generally is the reduction factor between the motionally averaged delta bar, over delta. Then I know for CH dipolar coupling, the autoparameter for methyl groups is minus 1/3. And the autoparameter for HH would be minus 1/2 if you were to do that experiment. I hope this part, how we got this expression at all, is somewhat clear. Basically, you get this motionally average anisotropy parameter by considering what happens when a magnetic field is along the symmetry axis. All right. Okay, so now I want to go to a, in a sense, more general situation for two-side jumps, because I'm not invoking these somewhat specialized equations anymore. Two-side jumps happen when you have ring flips. Two-side jumps averaging a uniaxial interaction. So I want to start out with a interaction which is easier, dipolar or quadrupolar. CSA is complicated. All right, so the goal is to calculate the frequency when the magnetic field is parallel to the three principal axes of the average tensor. So it's still the same principle. I will still like to somehow figure out the average tensor. And if I know which way my average tensor's principal axis point, then I can figure out the principal values by imagining my B0 field is along these three axes. So how do I establish the average tensor for a two-side jump? For a two-side jump, the average tensor should be a tensor that's invariant under the switch of A and B. Your two sides is state A, state B. Average means it doesn't matter whether you're talking about A, B, or BA. So that's the property of average tensor. So by symmetry, just based on that argument, you would say, okay, then if my initial direction is ZA and the final direction is ZB, well, I'm going to have one principal axis, which is the bisector of the two. That's going to be invariant under averaging. And then another vector is going to be perpendicular to the plane established by A and B. That's invariant. And then the third one comes out, is going to be in the plane perpendicular to the bisector. So just by symmetry, that the sigma tensor, average tensor should be invariant and the AB switching, that must be the situation. So that's good. So that means the sigma 1 axis is at an angle of beta divided by 2 with respect to both A and B. And what is beta? Beta is the reorientation angle, initial to final. And the sigma 2 axis, that's this one, then you can write down, okay, 90 degree plus half beta or 90 degree minus. And the sigma 3 axis is perpendicular, so it's 90 degree. There's a little bit of detail, 1, 2, 3. How do you count 1, 2, 3? There's a certain convention from left to right, which way you want to organize your principal value. Omega 1 is greater than omega 2, greater than omega 3 for the average. So there's a certain convention, just like your chemical shift, X, Y, Z, how do you define? You have to follow strictly. Okay, so if your beta is smaller than 90 versus larger than 90 orientation angle, you need to follow that convention, then it kind of switches what you call sigma 1, sigma 2, right? So we won't worry about that detail and focus on the concept. The three principal values of the average tensor, in general, omega n average, n meaning 1, 2, 3, is 1/2 delta and then 3 cosine squared theta n, theta are these angles, minus 1. All right. Let's just look at how we can apply this concept. So let's really look at a Fenelon ring flip, two side jumps. Although the ring flip around the torsional bond is 180-degree rotation, for the initial and final position of the vectors, it is not 180-degree. So imagine I care about measuring CH dipolar coupling, or in the old days, maybe deuterium NMR, I have a CD bond here, and my ring is flipping rapidly. Well, the initial position is here, and when it's done the 180-degree, it has gone to this place. That means my reorientation angle beta is 120 degrees. And this is true for this ortho CH group, and for the meta, it's not true for this para, because that motional axis is pointing along para, nothing changes, you won't see anything. Okay, let me just think about these bonds then. Well, this is a two-side jump, and so I can rattle off what are the three principal axes of my average tensor. There's the bisector, there's the perpendicular to the bisector, and then there's the sigma 3 sticking out perpendicular to the plane of the aromatic ring. And then I can write down my theta angles, 30-degree, 60-degree, 90-degree. For, this would be a 60-degree situation, this would be 30 degrees. So sigma 1 axis has an angle of 30 to the initial vector, and then you have second one and third one like this. Okay, then taking this equation, omega n averaged, so the motionally averaged principal values follow this equation, then you get omega 1 average coming out to be 5/2 of delta, the original rigid limit coupling, omega 2, etc. And you work out the math. Okay, so this is rather special looking in terms of the values of the new principal values for the motionally averaged tensor. It is certainly no longer uniaxial, unlike the starting point where you just have dipolar coupling or deuterium quadrupole interaction. And so just exactly how non-uniaxial is it? Well, you can take these three principal values and follow the definition of what is eta, what is delta, and work it out. If you recall from the basic lecture, the eta describes how asymmetric the powder pattern looks. So it takes the difference between the y and the x principal values and divide it by the z principal value, basically. So if you work through that, you find that motionally averaged asymmetry parameter is 0.6, and the motionally averaged delta based on this is 5/2. So it's this value, 5/2 delta. So instead of a rigid limit dipolar coupling kind of a peg pattern like this with two horns, two side jumps, rapid two side jumps for Fenelon rings will give you a powder pattern looking like this. It has two components. Its second moment, or the overall line shape, is a bit narrower by 3/8, or it's basically 62%, you might say, of the full pattern that follows this delta average equals 5/2 delta. And this line shape looks complicated, because it's 0.6 for eta, and there's two patterns overlaid, so that's why it looks complicated. But if I draw how an eta equal to 0.6 single component transition will look like, it'll have a middle value that's lopsided closer to 1 than the other. So normally with pattern like this will be the z principal value x and y. And eta is by definition the principal value that is, let's say, y minus x divided by the z. And so assume everything add up to be an isotropic chemical shift of 0. All right, so that would be a situation. What I'm drawing is roughly speaking 0.6. But now imagine you have dipolar coupling, you have a symmetric inverted pattern. And so it's got to look like, and then you superimpose the two, and that's what you get. So this is an example where a certain geometry of motion generates an average tensor, which is no longer uniaxial, even though my starting point is a rigid limit uniaxial interaction. So if you now measure dipolar coupling for a CH group on a phenolene ring, which is rapidly flipping, you get an interesting effect. Another type of two-side jump is trans-gauche isomerization. And this usually happens, let me just consider a typical aliphatic group, CH2, this carbon bonded to two other carbons. Everything here involves tetrahedral angles. And trans-gauche isomerization, it's trans to gauche plus, gauche minus. And the reorientation angle here will be 109.5. So the beta is 109.5. In trans-gauche isomerization, you have this torsional motion and you're moving the proton positions and it's swapping between the two. And so if that happens, then the initial and final can be just pointing along these two CH bonds. And that means that my motionally average tensor should have one principal axis that bisects the tetrahedral angle, and one will be perpendicular to the CH2 plane, and then the other one is orthogonal to the two. So again, what will be the theta angles? 35.3, magic angle, 90, and so on. And you work out, following this equation, that the principal values for the average tensor should be this. Now, the magic angle, whenever that shows up, that's very easy, because the 1/2 3 cosine square theta minus 1 becomes 0. Okay, again, this is something in that review article, and I don't necessarily think that they worked out the average tensor, but by numerical simulations, you can also calculate these things. But it sure is nice to have an analytical understanding. You don't have to worry about everything done by numerical simulations. But you see that in the fast limit for trans-gauche isomerization, so you don't populate all 4 positions, you only work on exchanging these 2 positions. Then you get a 10 shape because now the motionally average tensor has a eta average equal to 1. I have 2 principal values that are opposite in sign, 1/2 delta minus 1/2 delta. And then I have a middle principal value, which is right in the middle of the 2 extremes. And so it's a 10 shape for you. So trans-gauche isomerization, this two-side jump will average my CH dipolar coupling by a factor of 2 in terms of the anisotropy parameter, and then the asymmetry parameter is 1. Okay, I keep going. I can give another example of two-side jumps that's actually coming from our research on histidine ring flip in influenza M2. Histidine, it's not a symmetric ring like phenylalanine. You have a 5-membered ring, and you have a CC bond here, and you have a CM bond, you have a CC. Let me imagine that if my ring is actually doing a pi flip, a 180 flip. If that's happening, then I can say, okay, if I want to measure how this impacts the CN dipolar coupling, this green bond, then before and after, it's going to flip around this beta gamma axis. So I have initial, final, and then I can, again, do this average tensor analysis, a bisector, and then a perpendicular to the bisector, and then something that's perpendicular to the plane. And once I establish that average tensor for that 180-degree jump, then I can say, okay, my beta angle here, I know it must be 2 times 57 degrees. Why is that 2 times 57 degrees? Because this is my motional axis, and I know just by the covalent geometry of the imidazole ring that there's an angle of 57 degrees between that CN bond and the CC bond. Okay, so my reorientation angle is 2 times that 57 degrees, so it's 114 degrees. And then this means I go on to write down the 3 theta angles, and I must have values like 33, 57, and then the third one is always 90. Then I find out, okay, what are these motionally averaged principal values? 1, 2, 3. And I go on to then figure out what is the motionally averaged delta. So it's going to be an order parameter 0.56, and then the eta average is something like this. So I can predict if my histidine ring is doing 180-degree flips, I should have a scaling of dipolar interaction to about 56% of the original. If I'm not watching the CN dipolar coupling, but CH dipolar coupling, and I still have the same motional axis along this C beta C gamma bond, then I would have to first figure out what's the angle of the CH bond to that motional axis. This is about 78 degrees. And so when my CH bond flips to the other side, it's 78 times 2, so it becomes 156. And you go through the same analysis, and you find out that delta average is only slightly scaled from the original. So it is not averaged by motion very much. And why is that?
This is something you can understand even without doing any calculation.
Because if your bond is almost perpendicular, nearly perpendicular to the axis, you flip to the other side, then this orientation of the bond hasn't really changed. And so you shouldn't be affected by motion, right? And that's depicted here. In an extreme other case, if you happen to have a bond that's along the motional axis, then nothing happens. You basically don't see the motion. So you can, for any geometries that you would like to define, you can use this formalism for two-side jumps and go quite far in predicting what kind of line shapes you should get. I don't want to get too bogged down by this. One can get very sophisticated, and there can be multi-side jumps and not just two sides. You can also have diffusive motions, not so discrete, not just a few two-side or three-side. You can have many sides, and that becomes complicated, and then you really have to go through some numerical simulations. About 10 years ago, we worked on a tryptophan Indo ring motion, and we measured all the parameters. You can measure things easily, and then how do you interpret gets complicated. And so we realized that the simplest model to interpret that is not a two-side jump, but it's actually torsional motion around both the C alpha C beta bond, which is the chi1 axis, as well as the C beta C gamma bond, which is the chi2 axis. And you have to have sort of biaxial Gaussian fluctuation. So this is a lot of detail. And that all comes from the fact that we are able to measure CH dipolar couplings and see how these couplings are narrowed compared to the rigid limit. And you say, okay, well, the various bonds in the Indo ring that are rigidly held with respect to each other, they're affected by some common motion. And I have to come up with a model that can agree with all of these bond orientations relative to that common motion. So there's a lot of Euler rotations that you have to work through, but the end result is interesting. So in that case, the math is worth it. And that is showing you what we learned, that the tryptophan ring in influenza M2 is doing this periodic Gaussian fluctuation. The chi1, chi2 angle is changing. And as a result, these Indo buckets, I call it the buckets, is swinging close to the histidine imidazole rings. And we think then you can have a cation pi interactions because this happens at low pH when the imidazole has become imidazolium. It's a positively charged ring, and you have cation pi interactions that can then influence the proton transfer or suspend the proton transfer, preventing the protons from dissociating from the imidazolium. So that's interesting. Now, uniaxial rotation, as I said, is one of these very high symmetry motions that make it easier to analyze the line shape. And I want to give you another example. Again, in the case of influenza M2, I showed you the animation for what happened with the amantadine small molecule. In this case, the amantadine molecular symmetry is very high. And so things become simple. Internally, this molecule is rigid, cannot do any internal fluctuation. But the whole molecule can move in a certain way. So it can rotate. The first order of motion that it can do really is rotating around its own molecular axis. And that molecular axis is the threefold symmetry axis of the fused adamantane rings. And so that's something you have to recognize. And the other thing is that this adamantane ring, everything is tetrahedral. Bond angles are always 109.5. And so that's very nice. And all these CH bonds are oriented either at tetrahedral angle 109.5 degrees, or you have three of these CH bonds that are parallel to the motional axis. If you count the bonds, you find, okay, there are 12 CH bonds that are at tetrahedral angle from the threefold molecular axis, and 3 of these are at 0 degree. If I can get hold of a deuterated adamantine ring, and I can measure deuterium NMR spectra, then I can say, well, I imagine that this molecule with such a high symmetry should be able to rotate it around its own molecular axis. And if that happens, then I can invoke these formalism that I just told you about and say for uniaxial rotation, eta average is 0, delta average should follow this equation. And if this angle is 109 degrees, then it comes out to be 1/3. Already, I mentioned this before, 1/3 is for 109 degree. So that's nice. These 12 CD bonds that are set at equatorial sort of orientation relative to the motional axis, their couplings should be scaled down by a factor of 3. Those 3 CD bonds that are parallel to the motional axis don't sense the motion, so they should be fully rigid. And then if you have the whole molecule is tilted, not only doing the motion around its own axis, but is precessing around an external axis, which is bilayer normal in this case, or channel axis, then this term here will be scaled by another one of these second Legendre polynomials, 1/2 3 cosine squared theta minus 1. That theta then becomes the angle between the motional axis and the external channel axis. So in that way, then I can observe the spectrum and see exactly how much my ring is tilted. Right? If it's tilted very little, then I should get more or less 40 kilohertz, 125. If it's tilted a lot, if it's tilted by 90 degrees, I should get half of the 40 and 125 because 1/2 3 cosine squared 90 minus 1 is minus 1/2. Okay, so I have a way then to figure out the tilt angle of the amantadine ring. And this is when we look at amantadine dynamics in lipid bilayers. In the absence of any proteins, you can already see the deuterium quadruple NMR spectrum, 40 kilohertz here. There's a little bit of the 125 kilohertz. That tells you the ring is vertical and it's doing rotation around its own molecular axis. If you go to high temperature, you see this pattern shrinks by almost a factor of 2, 18 kilohertz and 58 kilohertz. So at high temperature in the liquid crystalline phase, then this molecule is tilted and it's still doing this rotation around its own axis, but it's also rotating around the external axis. Now, because I cannot tell the sign of this 1/2, I have a scaling, and it can be either minus 1/2 or positive 1/2. We don't think the positive 1/2 is very likely because that means my whole ring is turning 90 degrees. But the other way, the positive 1/2 is established when your ring is tilted by just the right amount, 37 degrees. So 1/2 3 cosine squared 37 minus 1 is positive 1/2. So we think that's much more reasonable. So this is the kind of information you can get. And of course, then you say, okay, I'm going to have my proton channel in the membrane. How does this change the motion? Then you can figure out how the amantadine sits in the channel. So that's a lot of geometric thinking for analyzing how dynamics affects your NMR line shape. Unless you do deuterium NMR. We get line shapes by doing CH dipolar coupling measurement, which is basically a proxy for deuterium NMR, but I can do it under magic angle spinning in a side resolved way. And that's the dipshift experiment. It is not as perfect as deuterium NMR because usually I don't get the eta information easily. I get the delta, the anisotropy parameter as scaled by motion that I can get. So dipshift is the easiest way to get that line shape. Or I can do 2D correlation. I have a chemical shift dimension, I resolve the side, and then the indirect dimension, I sample the dipolar interaction. The way I do dipshift, I don't directly get eta average information. If I do Lie Goldberg CP, I can get that piece more easily. So there is a way to do it, but very few people have done it to the extent that the method can be pushed. Deuterium quadruple interaction for aliphatic groups has the electric field gradient tensor, which is more or less pointing along the CD bonds. If you start to deviate from the aliphatic assumption, if you have other complicated nitrogen attached and so on, then it may not be that way anymore. It really depends on the electric field gradient tensor. So if you have ND groups, it's also close enough to eta equal to 0. It's not exactly. I think the ND groups eta may be 0.1 or something like that. So people have studied this before. I think this why it's close to eta equal to 0. I think the electric field gradient must be symmetric enough around CH groups or CD groups for it to be relatively close to uniaxial. Deuterium NMR is very old, and that's when people used to do site-specific deuteration. That's why it's not used very much. That's why I invoke this to illustrate the principle, and then I always do dipolar version. Because with dipolar detection, I can extend it to multidimensional, not just 2D, but 3D. I can have one dimension which samples the dipolar interaction, and then I have 2 dimensions to resolve the signals. If it's a large protein, it would be hard to do static NMR, but then the deuterium quadrupole coupling is rigid limit is about 110 kilohertz. It's very large, so you can still spin and get sidebands to up your sensitivity and still get at that anisotropy information. So that is doable. So if there's a really important problem for which site-specific deuteration is worth it, then one can do it. The technique is there. So recently, my group has explored that a little bit. We deuterated celluloids, bacterial celluloids, and I say, let's develop methods to measure deuterium quadrupole coupling as averaged by whatever motion you have. And then I want to detect that on the carbon side because I want to be able to do multiple sites. And it's not easy. We published this, but spin 1, polarization transfer to spin 1/2, it's quite a beast. Yeah, and the rigid limit is 110 kilohertz. And if you have motion, of course, if it's a rock solid, who cares? So it's not moving, right? I want motion. And so maybe it becomes 50 kilohertz, 40 kilohertz, and it's still good. And then I say, okay, I want to see if I can take deuterium NMR and you have a deuterated proteins that you already are making. I should be able to resolve all of these with carbon, plane, and then I have a deuterium dimension. Imagine that I can get that motional information, right? So in principle, you can try, but I think it's hard for sensitivity reasons. And then if motion is really quite extensive, then maybe it becomes 20 kilohertz. And then meanwhile, if you're saying I'm spinning at 20 kilohertz, then you're starting to spin out that interaction, which is the thing you want to take advantage of. For the dip shift kind of measurements, I don't want to spin very fast because I'm sampling the dipolar interaction within the rotor period. So if I'm going too fast, I don't get to sense that anisotropy. But there are other experiments where I actively recouple the dipolar coupling, in which case spinning speed is not so limiting. So I want to present the relatively easy experiment because it's very easy, they get used a lot. Dip shift stands for dipolar chemical shift correlation. And the goal is to measure lots of dipolar couplings as resolved by chemical shift. This is the so-called separated local field interaction because I'm having a 2-dimensional experiment where one axis is one local field chemical shift, and the other axis is a different one. It's a dipolar coupling. So in that sense, it's separate local field. This experiment was developed originally in the Griffin group by Monowitz, and my group probably uses it most extensively. It's easiest to be used by measuring dipolar coupling between proton and something else, carbon or nitrogen. So CH or NH dip shift. When you're not spinning too fast, you have to remove the proton-proton dipolar coupling. How do you do this? You start with a proton to carbon or XCP to get the magnetization on the X spin. And then you want to have a Hahn echo period. You have a pi pulse in the middle. And the period is overall 2 rotor periods. And in the first rotor period, instead of doing heteronuclear dipolar decoupling, where you shut down the proton pathway to the X spin, you leave alive the proton dipolar coupling to X by not doing heteronuclear decoupling. But you do something else, you do homonuclear decoupling for a period of time. So this orange block, homonuclear decoupling, can be accomplished by various homonuclear decoupling sequences. And the most convenient one these days that we use is frequency switch Lie Goldberg. So you remove the proton-proton dipolar coupling, but you leave alive the proton X heteronuclear dipolar coupling. And then your dipolar evolution is dictated by incrementing this period T1. That's dictated by how long that homonuclear decoupling sequence is. And then once that's done, you then resume your normal heteronuclear decoupling. So your T1 goes from 0 up to one rotor period. One rotor period is here. So since a rotor period is not that long, and your stepwise increment of the T1 should be maybe every 10 microseconds or so, you don't need many T1 time points before you get to the rotor period. Maybe 10 points, maybe a few more. Okay, so it's a very short 2D. You basically sample around 10 points or so, dipolar interaction, the heteronuclear proton-carbon, proton-nitrogen dipolar interaction. And then after that, the rest is heteronuclear decoupled, then chemical shift is refocused. Good, then you're ready for X-spin chemical shift in a T2 dimension. So that's the Dipship experiment. Direct detection, you do your normal resolved chemical shift, resolved map, your carbon spectrum. And then in indirect dimension, you have dipolar coupling being sampled. So the spectrum you get in the carbon dimension, and then this is the indirect dimension. This is where you have CH or NH dipolar coupling active. You Fourier transform the direct dimension, you get your normal, lots of peaks, right? Whatever the pattern, you can resolve things. And in the indirect dimension, if I haven't done Fourier transform, I literally have time oscillation. And I'm having time oscillations of this kind. And I'll show you why this is so. And you have a few points. So I want to have a mixed dimension data set. Okay, this is my omega-2, and this is my T1. So I don't even want a Fourier transform. You could, but it doesn't tell you anything more than what the time domain signal is telling you. Okay, so now taking that, we analyze and fit this time oscillation. And the idea is that if you have some of these carbons that are dynamic and other ones are rigid, then they will have a different pattern. So the something which is dynamic will have a shallow decay. Something which is rigid would have a decay. Right? And if you have something which is almost isotropic, it wouldn't decay. It would just be more or less flat. And so this is what you would expect for what's happening to an anisotropic interaction within the magic angle, spinning just one rotor period. Time 0, there's no anisotropy, high intensity. Time rotor period, high intensity. Time 1/2 rotor period, this is when you have the most pronounced anisotropy. Usually it's the lowest point. And then you have these points, okay? There's a double dip shift. Let me just quickly say, if you say, well, I need to spin faster because I'm at high field. If I spin too slow, the line width is not so good. And if you're spinning at 15 kilohertz and the interaction you're interested in due to motion has become pretty small, only 5 kilohertz, then you can imagine that interaction is kind of weak and you're spinning too fast, you don't see enough effect. So to overcome that problem, we say, well, I want to amplify my dipolar coupling in some way. I want to accumulate the effect of that dipolar coupling. And one way you can do this is the so-called double dip shift experiment, where instead of using the length of the homonuclear decoupling periods to define my T1, the active dipolar interaction, I fill one rotor period with homonuclear decoupling. And then on the X channel, I move a pi pulse from the beginning of the rotor period gradually towards the middle. And then I have a second pi pulse in the second rotor period moving from the beginning towards the end. And so these two pi pulses move synchronously. And the reason I want to do that is because I want to generate the heteronuclear dipolar coupling by having that 180 pulse changing the sign of the XH dipolar coupling. So it's the same trick in a sense as Redor, where you have 0 to T1 omega T, and then if you have a pi pulse, that switches the sign T1 to tau R, and the second part of the rotor period is basically the negative of the first part. And then because this negative sign here, well, you have 2 negative, then you basically get 2 times the effect of the dipolar phase. And so what this means is that by doing this pi pulse in the middle, you amplify the effect of the dipolar coupling and the somewhat fast spinning speed. So it allows motionally average coupling to be measured more easily at fast MES. Okay, so that's the detail for a better implementation, and we these days use that doubled version all the time. So this is the dip shift pattern or time domain curve you should expect to see. This is all simulations for certain spinning speed you choose. Let's say you're measuring CH dipolar couplings and you have homonuclear decoupling by FSLG. So that scales the dipolar coupling by a certain scaling factor, so that's fine. But the point of interest in the end is to see if my molecule is moving. And that order parameter due to motion averaging SCH is what's really interesting. So let's think about a rigid limit case. When nothing is moving, the order parameter is 1. Then under my experimental condition, double dip shift 2 times, and I have a scaling factor 0.577, that almost gives me back 1.1 and so on, then you would expect a rigid moiety to have the deepest dephasing. That's always the case. High anisotropy, strong anisotropy means your signal will decay deeply and rapidly. And if you have motion that reduce the coupling, then you have these curves decaying less. And in the limit of no coupling due to isotropic motion, then you have no decay. So these simulations can be made quite easily, and it's going to depend on the spinning speed, because if you spin, let's say, slower, 7 kilohertz, then you have a longer rotor period. Then you see the oscillation pattern, the time-dependent intensities to be different. So that's the dipshift experiment. You can go to my group's website if you're interested in implementing this experiment. It's really not hard to do. It's one of the easier 2D experiments because it's a 2D with only about 10 slices. Imagine you're measuring 10 1D carbon spectra. So it's really easy to do. And it gives you immediate information about whether something is dynamic or not. And so I want to show you an application. So in my group, we have studied plant cell walls quite a bit. And plant cell walls contain a lot of polysaccharides, and cellulose is quite rigid, but most other matrix polysaccharides are dynamic at different degrees of motion. And so cellulose is this 1,4 linked beta glucose polymer, but homogalacturanin is one of these matrix polysaccharides that are very, very dynamic. And so when we measure the carbon-13 NMR spectra, and then we do a 2D dip shift, we can measure these curves. And you see these are about a dozen time points. And you can see there's really quite a significant variation.
In terms of how deep these dip shift curves can be,
I don't have a rigid limit case, but by simulating these intensity decays, you can get all the parameters SCH. If you look at the cellulose, we don't look at because cellulose is always rigid, then it's a very deep curve. These are actually the fit value for the dipolar coupling strength. These are doubled dip shift experiments. So if you take the rigid limit CH bond to be 23.0 kilohertz, then 2 times that is 46 kilohertz. But then because we're doing homonuclear decoupling, there's a scaling factor of 0.577, then you're back to about 20-something kilohertz as a rigid limit. And then compared to that, they say, okay, I'm fitting my curve and I'm getting 17 kilohertz. And that's why 17 divided by the rigid limit value, that gives me the order parameters. What we usually learn from this kind of data is that there's different degrees of motion for different polymers. And then this motion also depends on the plant. So if you have a wild type, normal Arabidopsis plant versus some chemically modified mutant plant, which our collaborator devises, in one mutant, they say, okay, we have reduced the amount of methyl ester groups in this homogalacturanin. So methyl esters are these things. And if they remove or reduce the amount of that, they find that the plant is a dwarf plant. It grows small. And so you say, okay, that's great. There's a phenotype, and we would like to understand why on a molecular level, what's happening to the carbohydrate or polysaccharide in the cell wall that's making the plant a dwarf. The idea being for a plant to grow big, the cell walls have to allow the plant cells to expand. The cell walls have to be able to adapt and loosen. And for cell walls to loosen, you have polysaccharide that making this whole network of cellulose, matrix polysaccharides. If these polymers cannot move past each other and slip and do all that, then the cell walls will be rigid and they will hold your plant cells and your plant can't grow. This idea of the architecture of the polysaccharides, many different kinds of polysaccharide in the cell wall, that whole architecture has to be able to loosen in order for the plant to expand and grow. So for rapidly growing plants, the new leaves that are coming out and so on, the carbohydrates are very, very dynamic. The older part of a plant, the stem, the hard, woody part of the plant, those tend to have less dynamics, which you can measure from exactly this type of experiment. So you can relate molecular dynamic properties to how this plant grows. That's pretty nice. In wild type Arabidopsis, you have cellulose that are rigid. They are the scaffold of the cell wall. And then you have all sorts of matrix polysaccharides in between. And then you have this low methyl ester mutant. And you have, these are the NMR observed results, more dynamic side chains, and you have stronger pectin cellulose interactions here. So some of the sites, the mutant has become more rigid. And when we assigned which peaks these are, we attribute those to those part of the pectins that are interacting with cellulose. You see in my picture here, these pectin chains, the brown chains, the green chains, they're not particularly drawn to be close to the cellulose, and that's what I want to convey, that in the mutant, you have certain portion of pectin that's holding on to the cellulose very well. And that's going to prevent the slip that needs to happen in order for the cell wall to loosen. That's the kind of insight we get. I can skip the Lee Goldberg CP. This is pretty dense. It's a different way of measuring CH dipolar couplings as a way of looking at motion. Yeah, okay, let's take a break.